Dear students, in this chapter, Chemical Bonding and Molecular Structure, we will study about the various types of bonding and the shapes of the molecular structures. But before starting the bonding and the Lewis dot structure, let me tell you that matter is made up of one or the different types of elements, and elements are made up of atoms and molecules. But atoms are incapable of independent existence except the noble gases. Otherwise, all other atoms, all other elements, they exist in the molecular state. Now, why these noble gases are capable of independent existence whereas the other atoms cannot do so? The reason behind is the noble gases have their 8 electrons in their valence shell, and all other elements, they do not have 8 electrons in the valence shell. So these atoms combine to enter into more stable state. There are many theories given regarding the bonding of the atoms. For example, the valence bond theory, the molecular orbital theory, valence shell electron pair repulsion theory, and the Cossel-Lewis approach. Normally, there are two types of bonds, the ionic or the electrovalent bond and a covalent bond. Ionic bond and covalent bond we will discuss now. Ionic bond. Ionic bond is formed by the complete transference of one or the more electrons from one atom to another, and this process is called electrovalency, and the chemical bond formed is termed as the ionic bond or the electrovalent bond. By sharing of electrons, a covalent bond is formed. A covalent bond, when 1-to-1 electron is shared, then it is a normal covalent bond. But in a special type of sharing, when both the electrons are contributed by one atom, it is a coordinate bond, a special type of covalent bond. So let's have an overview of the two types of bonds. There are two bond types, ionic and covalent. In ionic bonding, one atom has stronger attraction for electrons than the other, and it steals an electron from a second atom. In covalent bonding, the attraction for the electrons is similar for the two atoms. They share their electrons to obtain an octet. Cossel and Lewis studied the nature of the noble gases, and they come to the conclusion that noble gases do not undergo the chemical combination because of their complete octet. And they also inferred that only the valence electrons, they play a role in the formation of the chemical bonding. The inner electrons do not participate in the chemical bonding. So, while representing a chemical bond, that is an ionic or a covalent bond, Lewis gave a Lewis dot formula, or he gave the Lewis symbols, in which he represented the valence electrons through dots, and that is why they are known as the Lewis dot structures or the Lewis dot symbols. The first group element have only one electron in their valence shell, and that will participate in the chemical bonding. So, we will write the symbol of the element and put one dot. One dot means one electron. Similarly, the second group has the two valence electrons. So, again we will write the symbol of the element, for example beryllium, and we will show two dots. The two dots will represent the two electrons. In the same way, for example, in the case of oxygen, the atomic number of oxygen is 8. So, in its valence shell, it has 6 electrons. So, we will put 6 dots around an oxygen symbol. This is the very simple method to show the valence electrons, and it make it very simpler to show the chemical bonding through these Lewis dot structures. Neon. Neon is a noble gas. It has 8 electrons in the outermost shell. From the picture also you can see the 8 dots around the symbol of the neon element. Rubidium, only 1 electron is shown, that is via 1 dot. Around the fluorine there are 7 dots, means there are 7 valence electrons and only these electrons will participate in the bond formation. It may be a ionic bond or a covalent bond. Now I'll tell you how to write the Lewis dot structure in a case of a chemical compound. First of all, what we do is we total the number of the valence electrons. For example, in the case of the carbon monoxide, that is CO, the carbon has 4 valence electrons and oxygen has 6 valence electrons. So, 4 plus 6 equals to 10 valence electrons. Now, we intelligently guess the structure of the carbon monoxide molecule. Then we will write the symbol of carbon and oxygen and then distribute the 10 electrons around these elements. As per the rules, the lesser electronegative element comes in the center and the more electronegative elements surrounds the lesser electronegative elements. When we show the electrons, first of all we make the single bond. That is, a single bond is formed by the sharing of the 2 electrons. And if the electrons are left even after the formation of the single bond, we make the double bond or we show the leftover electrons through the lone pair of electrons. Let me revise through these. Counting the total electrons. Once we have determined the basic structure of the molecule, we can start placing electrons around atoms. The first step is to determine the total number of electrons that are available. We use the group number of the element to indicate the number of the valence electrons that it contributes to the molecule. Example, oxygen in group 6A contributes 6 electrons. Once we have determined the number of the total valence electrons, we can start distributing them throughout the molecule. When we represent electrons, they will be in pairs, since an orbital holds 2 electrons. Electron pairs can be represented with 2 dots or a solid line. Ionic bonding. Now I will explain ionic bond through a Lewis dot structure, that how we can represent an ionic bond via Lewis dot symbols. For example, ionic bond in sodium chloride. Sodium has 1 electron extra, that is more than an inner octet. So, it tends to lose this 1 outer electron to the chlorine, which has 7 electrons in the valence shell. Both do this to have 8 electron in their octet. Sodium loses 1 electron and changes into sodium cation, that is with 1 positive charge, whereas chlorine gains 1 electron and completes its octet and changes into chloride ion. Now let me show you this through an electron dot symbol. The transfer of electron you can very well see from the sodium to chlorine and entering of them into the more stable state. And since they are now oppositely charged ions, electrostatic force will hold them. You can see the electron dot structure now. The chlorine is surrounded by 8 dots. 8 dots means 8 electrons around it. And now also you can see a negative charge on the chloride ion because it has gained 1 electron from the sodium ion, and sodium has 1 positive charge. Now I am taking another example of lithium chloride. Lithium, an alkali metal, again it has 1 electron in the valence shell, and the chlorine, it has 7 electrons in its valence shell. the one valence electron of the lithium will be transferred to the chlorine, and chlorine will change into chloride ion and lithium will change into lithium plus cation. One electron is transferred from the lithium to the valence shell of chlorine. Now, lithium has 2 electrons in its valence shell and chloride ion has 8 electrons in the valence shell. After the octet, the duplet state is stable. So, lithium completes its duplet because it cannot complete its octet. Now, let us see the electron dot structure of lithium chloride. That lithium has 1 electron in the valence shell which is transferred to the chlorine atom. Chlorine has 7 electrons, the 7 dots you can very well see. Now, you can understand how we can represent the electron dot structure and the ionic bond. Let me take another example of methane to show the electron dot structure. Carbon, it has 4 electrons in the valence shell and hydrogen has 1 electron each. Now, they will form a covalent bond, a bond which is formed by the sharing of electron. The red dots, they are representing the single electron of the hydrogen and the black dots, they are the 4 electrons of the carbon. Now, you can see that by the sharing of these electrons, the duplet of the hydrogen is complete and the octet of the carbon is complete. Both are in the stable state and electrons are represented by the red and the green dots. Lewis dot structure is a very simple and very convenient method to show the sharing of electrons. This is an example of ammonia. In ammonia also, nitrogen will complete its octet and hydrogen will complete its duplet. Now, the octet rule. From last so many examples, it is very much clear that to complete the octet is the most stable state. The noble gases have their octet complete and all other elements, they enter into this most stable state. So, octet rule states that the atoms of the different elements combine with each other in order to complete their respective octets, that is 8 electrons in their outermost shell, or duplet, that is having 2 electrons in the outermost shell to attain stable nearest noble gas configuration. Dear children, but there are limitations to the octet rule. There are many elements which cannot complete their octet. There are many elements which have electrons more than 8 in the valence shell, that is known as expanded octet, and there are elements which have odd number of electrons. Let me give you quick examples of these 3 exceptions to the octet rule. The incomplete octet of the central atom. The number of electrons surrounding the central atom is less than 8. This is especially the case with elements having less than 4 valence electrons. Most common examples are the compounds of lithium, beryllium and boron. In these, the central atom, they do not complete their octet, they complete their duplet. This is the first exception to octet rule. Odd electron molecules. Nitric oxide has odd number of electrons. Similarly, nitrogen dioxide, the octet rule is not satisfied for all the atoms. The expanded octet. Expanded octet means the number of electrons in the valence shell is more than 8. For example, in PCl5. In PCl5, phosphorus is in the center and instead of 8, it is surrounded by 10 valence electrons. Let me show you through the atomic model set. This is PCl5. Here, the black atom is representing phosphorus. It is surrounded by 5 chlorine atoms. Now, you can see these single bonds. The shape is trigonal bipyramidal. Here, these 5 bonds means the 10 pair of electrons which are surrounding this phosphorus atom. One bond means 2 electrons. In total, there are 5 bonds. 2 into 5 means 10 electrons are surrounding the phosphorus. Octet rule says that there must be 8 electrons around the central atom. But in PCl5, there are 10 electrons around the central atom. Let me take one more example of SF6. This is SF6, that is sulfur hexafluoride. Here the black ball is representing the sulfur atom. It is surrounded by 6 fluorine atoms and these are 6 covalent bonds. 6 covalent bond means 12 electrons are surrounding the sulfur atom. Again, this is an exception to octet rule. Let's see the electron dot structures of all these exceptions. PF5, this is phosphorus pentafluoride. Phosphorus is in the center, surrounded by 5 fluorine atoms. Now you can see the 5 covalent bonds around the phosphorus. So you can very well count the number of electrons around phosphorus. It will be 10 in number. Other drawbacks of the octet theory are, this theory does not account for the shape of the molecules. It does not explain the relative stability of the molecules, being totally silent about the energy of a molecule. Dear children, let me give you a quick recap of this topic. We studied that why do these elements combine and how do they combine. We also studied the Lewis dot structure. Lewis gave a very convenient, very easy method to represent the valence electrons by making dots. By showing the dots, we can very well see the ionic bond formation and the covalent bonds. We also studied about the octet rule and its exceptions. There are many elements who complete their octet, but there are few who have either less than 8 electrons around them or more than 8 electrons around them. I am sure all these concepts are clear to you.